Now this is a unit I picked up about a week ago at a ham fest, and why? Well, look at that, 100,000 volts. Nice. Now you can get a few delightfully dangerous voltages with, say, a microwave oven transformer. You can get 2, 3, 4, depending on how you organise it, even 8 if you stick two of them together. Or you can get 25, maybe 30,000 volts out of a flyback transformer. But 100,000 volts is a completely different realm. So yeah, that's what attracted me. And I took the all offer, got it for 40. And while I was thinking about what I should be offering, I missed out on a couple of red flags. So I think I actually got ripped off. I should have twigged that this bit of cable that came with it, I doubt can be trusted to handle 100,000 volts. And on the back, this output socket is also highly doubtful for 100,000 volts, I would imagine. And then if we look at the model number, AU-3P400, the 3 stands for 3,000 volts. So I think that's what this really is, 3,000 volts, not 100,000. It's made by Matsuada Precision. It does look pretty nice. It seems to have two 4-digit displays, which I presume are for setting the voltage and the current. It's quite stiff to turn, that one. So let's have a look inside. We'll have a look at the back first. On the back we've got the output, the ground screw, a DB25 and a link that's been wired across, ventilation, and this also looks like mains in, yeah, that's the mains input there. Neutral, live, ground, don't know what that one's for, and 15 amp fuse. It also came with this bit of wire, so I haven't got a plug, or maybe, oh sorry, no, it does have a plug. So I'm a bit sus of this wire being good for 100,000, but maybe 3 is plausible, and it's got a plug there, so we'll be able to monitor what comes out. But before turning this thing on, I certainly want to see what's inside of it, if for nothing else to make sure that touching this case will not be dangerous. Looks like 3 bolts to get the top lid off, and we'll see what's in there. I was thinking it's just a top plate, but it's a U-shaped top cover, so there's also 4 screws on the sides to undo. They're off now. Let's lift the lid. More potted stuff, but I suppose you expect that for high voltage, but there's a lot in there, isn't there? And we've got a box of spare tricks, some speed nuts, don't know where they go. Wow, lots of silicone, 2 levels of that, another one down there, and down there. Gee, makes you wonder if it is 100,000. Big transformer, look like diodes. So the volts come in here, filtering, mobs, big dual choke, MOSFETs probably, and the part numbers haven't been sanded off, so that's nice to see. Ferrite transformer, a few more small transformers, big transformer. The power comes in from the filter to the main switch to here, and I'm guessing would go to this bridge rectifier. There's some more smarts down there that connect to the front panel. There's looks like a digital board down the bottom. Yeah, so here presumably through the bridge rectifier into these bulk filter capacitors. The controller oscillates these transistors, a lot of them, driving the primary of this guy, and that looks like this wire, so probably fairly high frequency, and that goes into the nasty section. This board's got a big plus and minus on it. What are these? Voltage multipliers? So, should I turn it on? I'll try and rig up something to measure the voltage coming out of it. last terminal doesn't go anywhere. So the ground terminal connects to the frame. There's also a bunch of grounds going to that wing nut at the rear. And of course a fan to go from the vents past the transformer to the electronics, or vice versa. Probably vice versa. There's vents over here on the cover, so presumably it draws air in there, past all the electronics, past the transformer and out the back. I might lift off that top board, big L-shaped board, just to see what's underneath. Right, I've taken the screws out of this big board. Good, it folds away like that quite nicely. So, the output is there. The input comes from the transformer via this board, or via part of this board. Yeah, there's two distinct halves looking at the trace down there. That's all one thing, this is another. So, goes into this, presumably comes out here, along with the other input from the transformer, into this gizmo, and then that goes upstairs to this guy, and then it looks like they haven't cleaned the solder off, and then that goes into the next stage up here, and then that goes down into this one out there. So is that just a whole bunch of triplers or voltage doublers or something? I can measure voltages at stages along the way and see what happens at each point, but not right now. First we'll just put this back and gently turn it on. Put two of these bolts back for the moment. Just looking at the digital side of things, that digital board down there connects to the display, obviously, and the two voltage and current controls also go to that board, and there's also, of course, a cable between the decks from the digital up to the driver board. There's also two more cables down on the digital board going around to here, one to the DB25 on the back and one to this little board. I'm guessing that's feedback from the output of the unit to the control board, so it can monitor its output and adjust. These 6 standoffs that hold the top board up are obviously earthed. There's not much separation from the standoffs to this line here, and this one, unless it's ground. We've got nylon screws there that hold the potted blobs down. Screw that board down again and stick some bolts in and see what happens. Now, I keep making excuses for doing something else before turning this on, and that's because it might be the last video I ever make. And I've given instructions in my will that the remainder of this video be uploaded if something untoward happens, so I'll try and get out as much as I can before I turn it on and stick any bolts in. I was interested in knowing what to expect coming out there, so I wanted to know more about the topology of what's going on here. So I've unplugged those, and I can take this board out and try and draw a wiring diagram of what's going on here. Now, this is just resistors in series with diodes. These are 7.2 kilovolt diodes, so they're in series, and then 2 or 3 of them are in parallel, and then they're all in parallel. So these are just great big diodes with ballast resistors. I'll measure those. They should be pretty low resistance, I think, just to share the current equally amongst all the diodes, but basically they're all in parallel, and there's 2 sets of them, one there and there. And these terminal strips, although they've got many pins, only two or a few of them are used on each one, and some of them go nowhere. There's no trace connected to that. So yeah, try and draw out what's going on in all this. Also interesting is down here there's quite a few what look like neons. There's 4 little ones and a big one, and their designators are AG1, etc. All starting with AG. I'm not sure what that stands for. But yeah, a couple of relays there. bit of a bodge here and there. I'll try and draw out the circuit for all this, try and get a clearer picture of what's going on. I didn't get too far with tracing out the wiring of this thing because I didn't want to lift off the bottom board and see what the connections are underneath that. And there's a lot of small connections inside each block going to the printed circuit board, but just going back into the block. But you can look at the major wiring, like these white wires and these traces here, and I've come up with something like this. So this is the big transformer over here, goes into this pair of diodes. That's all that is, just two diodes. They and the other side of the transformer go into block number 1 down the bottom, and from then on it's something like this. There's other wiring as well, but these are the major ones, those traces and the white wires. And finally the bottom block down here goes to the output, and this wire here from the top block I believe is the output voltage monitoring, or perhaps there's other connections from this that I can't see, I don't know, on that bottom board that go into the circuitry that feed back to the controller, so it can adjust the duty cycle to keep the output voltage constant. Now if you look at this, that's wrong. Minus and plus don't fit the way the diodes are pointing. It's just minus and plus here. And this is the cathode. These marks, I've checked the data sheet on these diodes, which by the way are 300 milliamps, 7.2 kV, and these are 10 ohm resistors. That should be the negative if the diode's coming that way from the transformer. This P in the model number indicates a positive output voltage, so it's positive with respect to ground on the case, but you can make it negative, then it would be an N in the model number. And unfortunately the only manual I've been able to find is for a later variant of these things, which this section is completely different, but you can rearrange the wiring to make this a negative output. And I'm thinking on this one perhaps you might have to do that by lifting these connectors and then perhaps reversing that board to make it a negative output. I'm just guessing there. And and you'll notice here there's a wire coming out of here, goes into one terminal on that strip and then out to that. You see how daisy chains from 2 terminals on each of those 4 connectors. So that's some sort of an interlock to check that the wiring has been plugged in. So if these aren't plugged in, it won't run the power supply. So I guess it's just to make sure that if you have fiddled with the output polarity that you put everything back properly. Bit of rambling, I know, but just discovering bits as I go. There seems to be something underneath this potted glob. Looks almost like trim pots, but I'm not sure what they are. There's something under there which has been sealed over. And a few other things I've noticed. On the back there is the instruction manual, shows what this is for. There's inputs there for controlling the voltage and current, just 0 to 10 volts goes through the full range. There's also signals coming out 0 to 10 volts indicating what the current and voltage are. There's a 10.24 volt reference output which you can use for the voltage and current control inputs. This switch, this S2 here, is intended to connect to some door mechanism, a switch on a door on the equipment that this is connected to. So it's just an interlock, so that when you open the door the power supply cuts off, and if you don't want that then you short them together. In here, remember I saw some things that looked like neon bulbs down in there. Well, there's a, try and light this up. There's one there, in fact there's a whole lot of them down there. Yeah, there's behind that ribbon cable. See, there's a group of them. Don't know what they're about, but seems to be a common, maybe they're spark gaps. I suspect they're just neon bulbs though that will conduct when voltage is too high and stop bad things happening, or limit them. And the mains power goes through the main switch into here, which I guess goes to the bridge rectifier into there, but it also goes down to that bottom board, the digital board. I'm not sure why they would want 340 volts of DC down there. Why not put that? I'm guessing maybe there wasn't room up here to put the switching power supply on here as well. So that looks like it goes to a switching power supply down on a digital board. I'm not going to take that out. It's be a bit of a job to unplug all this and undo these screws down here and lift that whole aluminium section up to see what's going on this bottom board. I'll only do that if I have to. Might be time to finally get around to switching this thing on. Okay, for that I've got to put on a AC cord there. It doesn't say what sort of wire this is. It's 5mm, so that means it limits it down to a few. Solid core, looks like polyethylene insulation and braid. And I looked up a few cables that match that physically, and some of them seem to be good for 4 or 5 kilovolts. So, okay, maybe this is all right for this thing. And I've stripped off the end, ready to connect it to my little high voltage divider. Divided by 100, and we'll look at that output voltage on this. So I'll wire it up and yeah, see if I can electrocute myself. And after a bit of a panic with my camera being stuck with a lens error, which seems to have freed itself up, I can now record again. So here we are, all set up, ready to go. There's the power cord and the high voltage cable at the back to the high voltage divider to the A meter. So I'll turn the controls down there, we'll turn the meter on, I'll plug the power cord in and we'll see if anything sparks just from that. Okay, plugging in the power cord, watch out for sparks. Good, no sparks. So now I guess I just have to turn it on and hopefully we'll get a display here. Fans on, we've got a display, no kilovolts, no milliamps, and the Anning says no volts. Alright, so let's try turning this up a bit. Nothing. Constant current. Constant voltage. No, there's other indicators there that aren't coming on, so there's no error indicators. Maybe I have to turn the output on. No, that's not doing anything. So have I been sold a dud, bastard? Don't work. Okay, I'll have a look at the manual, see if I can get any clues, but from my understanding they should be changing as I turn these. Or there should be an error indicator. Output on the LED for the output's not coming on. Alright, I'll turn that off and have a little think. Well, I've had a look at the manual and I think I may have found the problem, or at least I hope I have. It's written in Japanese English, but despite that it's not too bad, though there is room for some improvement. Looking at the DB25 on the back panel, down here we have short equals external, open equals internal on pin 20. I took that to mean that if you left the thing unconnected completely, then it would run internal. But it looks like this short equals HV on is also relevant on pin 21. If we look a few pages further on, well, the next page, here's you've got to short those two to make it external. If you leave it open, it operates internally. That's what I thought anyway. But down here, a few pages further on, for the remote on off, this function is effective regardless of selection of internal or external. So it looks like I have to make that connection from pin 21 to pin 17. 17 being ground and 21 being the remote switch. So I've made a connector to do that and we can give it a try. Now if that's true, you'd think, well, on the next 6 pages describing this thing, they should point out on that first page, or the latest, on this second page, that this is in fact true. The function is effective regardless of internal and external. The next 6 pages mean nothing unless you connect this wire. Should say that, I reckon. Alright, plug this in, give it a shot. Okay, everything's ready to go. Turn these down. There's the output of the high voltage divider showing 1/100th of what's coming out. Turn on the power. And turn up the volt knob. I'll give it a bit of, put it into CV so the current's not limiting it. And then turn this up. And nothing. And some of these have a soft start option which makes it wait 10 seconds. But it looks like that's not what the problem is here. Oh, duh. Got to turn this on. Look at that. We have volts. So, 300 volts, 400. Let's go for 1,000. 1,000 volts. 2,000. What a dickhead. 2,000 volts. Let's go all the way. 3.07 kilovolts. 3,070 volts. Well, that thing looks like it works. Let's turn on, lower the current. And it dies. And I think it doesn't come back. You have to power off and on. Or, yeah. There's also a reset signal on the rear terminal that would do what I just did. It takes it out of current limit. Now it'd be interesting to have a look at waveforms on the oscilloscope. I might try that. This is good though, isn't it? Yay! Alright, now I've got the oscilloscope connected through the high voltage divider. Let's have a look at what waveforms we get out of it. Oscilloscope on, power supply on. This is, as it turns out, is not a, although it says constant current, that's an option apparently, or at least it's an option on the newer variant of this thing. As it sits, it's just a overcurrent cutout. Got to have some setting on that to go into constant voltage mode, and then we can turn up the volts. Turn on the output. See on the oscilloscope. A lot of that will be just artifacts from the oscilloscope. 1.5 kV, 15 volts. But as we vary the voltage, yeah. That's just oscilloscope. Change the. That's more like it. There's a bit of response lag, up to 3 kV. Not bad though. I'll put it to 1 kilovolt and switch to AC. And try and sync on something. Okay, looks like we've got some sort of a high frequency there. Wobbles around a bit, but say 100 megahertz, just roughly. Peak to peak, and of course multiply this by 100, so 2 volts peak to peak variation in 1,000. Not too bad, is it? And the next thing I want to do is give it a load. Go back to DC. I have to use this wooden block underneath of here for that. So turn this off. This thing can put out 400 milliamps, and at 3 kilovolts that is 1200 watts, and I do not have a 1200 watt 3 kilovolt resistor. What would it have to be? 7500 ohms, I think. 1200 watts. I don't have a resistor that does that, but I've got these which are I'm guessing say 100 watts. They're 2.5k each, so in series that's 5k, and I'll stick them on these two nails, stop them falling over, and then connect them to the output of the power supply like that. And I'll use this to measure the temperature on these guys. Voltage down, power on. Now I've got to give it a bit more current, of course. Now as I turn up the voltage, we'll get some current showing. Pretty soon it'll hit the overcurrent CC and it cuts out. So drop the voltage, and you've got to reset it by cycling the output. The resistors are coping with that pretty easily. I'll crank the current up some more and then try and get to a kilovolt. Cut out. Current up a bit more, power on. No, almost there, a bit more current, cycle power. Here we go. Kilovolt there, and doesn't look like any ripple. Again, let's go to the 8 and 200 milliamps, 5k. So these guys are getting hot now. 50 degrees C, 60. So we'll go to AC coupling. It's pretty good, it's not much worse. Went from 28 to 35. Of course, when it's running at half its output current, but that's pretty good, isn't it? And there's resistors 80, 90 on one of them, 100 degrees C on the other. This one pretty close, yeah, 100 degrees C. That's with kilovolt, 200 milliamps, which is what? 200 watts. So 100 watts each and 100 degrees C. So to test this at its full output power and full output current, I would need a big resistor, 1200 watt resistor, 7.5k. I might try one day to make a salt water resistor. See what this thing does then. But this seems pretty good. Bugger all ripple, really. 3 volts ripple in 1000 volts, outputting 200 watts. That's pretty good, I reckon. Alright, I think my resistors are cooked long enough. We'll wind this down. Constant current cut out. Would have been nice if it was constant, a real constant current instead of just an over current protection. But, oh well, you can't have everything. I reckon it's pretty good value for 40 bucks. I'll be able to do some experiments with insulation strength and testing protection devices like gas discharge tubes, see what voltage they cut out, they cut in at. I suppose I could do something nasty. I could put a couple of microwave oven capacitors on it and charge them up and have a spark gap. Should I do that? Yeah, let's have a look at that. Right, what I've got here is the ground still goes to the ground on the divider, but now the high voltage goes through this 47k resistor to a capacitor which is in series with another capacitor. So these capacitors are 1 microfarad, 2100 volts, so 2 of them in series is half a microfarad, 4000 volts, and the other side of that goes to ground. And I've got a little spark gap here. Now unfortunately this isn't as sparky as I thought it might be, but I've got a tiny little gap there, as close as I can make it, because any less and it just doesn't spark. And I've got the current set up fairly high. So yeah, there's the gap there, and here's the volts. So turning on the output, winding up the volts. You can also see it on the oscilloscope. And when we get enough volts, it'll spark across. There we go. And you see how the negative side gets quite hot? It's melted too far to even spark. or is it joined together? I'm getting 64 milliamps, so it looks like it's shorted. 2 kV, 35 milliamps. What's that? 70 watts, is it? And now we've got a nice little arc. It melted the metal and then stopped. Okay, zoomed in now. 3 kilovolt, 56 milliamps. Now we've got an arc as the metal melts away. And oh, there we go. Isn't that pretty? Now it's 40 milliamps. So that resistor will be getting pretty hot now, I think. Well, that resistor's 130 degrees C, 140. 3 kV, 30 milliamps. And that resistor is 160 C. I hope you found that interesting. That's about all I can do for now, I think. These controls here on the newer variant, these are 10-turn pots, and I suppose I might do the same thing, put 10-turn pots on there, and they also have a locking mechanism to lock them in place. I don't know about that, but 10 turns would be nice, get a bit finer control. 12, 15 millimeters now, and it just went out. And how hot did that resistor get? 200 degrees C. Alright, that's enough with this thing. I hope you found that interesting. Please don't forget to give it a like before you watch the video, and I'll catch you later.